Welcome to day 19 of the macOS and iOS Security Internals Advent Calendar. Today we will be looking into Mach Exceptions, what they are and how to deal with them. So one of the questions that a lot of people have is, there's this report crash daemon, but how does it actually work? How does it actually catch the exceptions so that it can then dump the crash logs to disk? Well, the magic is basically all coming from the Mach Exception server. So what is that? Within XGNU, or the Mach part of XGNU, there is this concept of exception ports. And the idea is that code can register an exception handler by registering an exception port with the system. And then when an exception happens, the kernel will send a message that contains information about the exception to this port, and whoever receives message on that port can handle as an exception server and handle the exception basically. There are different granularities how you can use that. There's a host-wide exception handler, which you can set via host sets exception ports. There is a task-wide exception handler, which you can set with task set exception ports. And then there's also a thread-wide exception handler that you set via thread set exception ports. So in the case of the report crash daemon, everything is done via the host exception ports, which are eventually stored in the real host variable of the kernel. So all these three XXX set exception ports functions have the same prototype. So it doesn't matter what granularity you choose, you always call them with the same arguments. The first parameter is basically the object that you are setting the exceptions for, the host, the task, or the thread. Then you specify the exception mask. That's basically a bit mask of what exception handler you are interested in. Then you set the port, which is the Mach port that receives the message from the kernel. Then you have a behavior. The behavior selects different kind of messages that the kernel can send to you that contain different aspects of the data of the exception. And the flavor in the end selects what kind of thread state you want the exception to come with, so that you can understand what's going on. So the exception mask selects which exceptions you are interested in, and it's basically a bit mask with the following bits, meaning different kind of exceptions. First of all, bit 0 is not used, it's reserved. And then bits 1 to 13 select what kind of exception we are interested in. So for example, the exception number 13 is the so-called abnormal process exit exception. This is what the report crash daemon, for example, makes use of. And then you have other stuff like bad access, bad instruction, Mach syscall, syscall breakpoints, resource problems, and so on. And these are then the other kind of exceptions that you can register exception handlers for. So the exception behavior defines what kind of message gets sent to you, and the valid values are exception default, exception state identity, exception identity protected. So the default just gives some information about the codes and the who caused the exception. When you have state, then you have also the CPU state inside the exception message. State identity is basically a combination of default and state, so you have both inside the exception message. And the identity protected is something where the identity, what task, what thread it is additionally protected. So there's also the Mach exception errors code here, but that's not used at the moment. The only thing that exists is here this exception codes that basically tells the system that we want to have two 64-bit codes inside the exception header that explains a little bit more about the exception. So let's look into the messages that you actually get as the server. So the ID number for the message is 2405 when you have a default exception behavior. Then this exception looks like this here. So basically what we have is we have the Mach header, we have the message body, but this is a complex message. So the message body is basically just the number 2 in this case. And then we have two port descriptors. So we get the thread port and we get the task port of whoever caused the exception. The NDR record is basically just to detect what system we are on, what endian is, so we can ignore that. Exception is basically the exception code. And then the additional information for the exception, we have the code count, which is usually 2, and then we have two 64-bit values that give us more information about the exception. So when you handle this exception, you need to send back a reply, and this reply packet should look like this here and has this 2505 code in it. But here there's nothing much, there's just the return code that is inside the message. So more interesting is when you have an exception state, because then the CPU state is a part of the message. But you can see here we have no longer a complex message. We don't have the task and thread ports. So in the state, we only have the actual CPU state. And the CPU state is basically encoded as what flavor it is, and then the actual data of the state. Again, if we want to answer this, we need to send a reply, which is 2506. And the reply also has a new state in it, so we can actually replace the registers before we continue execution of the after the exception. So we can actually fix the problem if that's possible, and then let the code run, for example, from a different position. So when you have state identity, it's basically a combination of those two. We have a complex message again, so we have the thread port and the task port again, but we also have the state in here. And again, this is 2407, so if we want to answer it, we send 2507. And that's basically the same thing again, but we have the state here, so we can again modify the state of the reply. And yeah, that's basically the options that are most used. So now what's about the thread states? Basically, the thread states depend on what CPU you are on. So if you're on ARM or on x86 64. So on ARM, the ARM thread state 64 is basically defined like this. You have all the X registers, then you have the frame pointer, the link register, the stack pointer, the program counter, the CPSR, and you have the flags. And the flags, for example, tell you if, for example, certain parts like the program counter or link register are pack protected. Yeah, that's basically it, more or less. So this thread state is flavor 6. So if you ask for flavor 6, this is what you would be able to get back. However, more common is actually that you get flavor 1. And flavor 1 is basically like a wrapper. It's the so-called ARM unified thread state. And the idea here is that in the thread state basically has a little header inside that gives us a subflavor and the amount of elements inside the subflavor. So you would be able to, for example, see a flavor 1, and inside you would have a flavor 6. So the ARM thread state 64 would be inside the unified state. If you ever encounter on an x86 system this this exception, then it would look like this here. You have basically a 64-bit exception, and you have all the 64-bit x86-64 registers here. So from RAX to RSP, then from R8 to R15, then you have the RIP, the RFlex, and then you have the segment registers CS, FS, and GS. Yeah, that's basically the thread state that you deal with on an x86-64 system. So, and now let's have a look at the kernel panic dump to see if we can see who registered the exception handlers. So let's have a look into the kernel panic dump to see what exception servers were installed. So we have to load the LLDB macros, and we go into scripting mode, and now we can just print xnu.kern.globals.realhost.exception actions. Let's print this out, and we see we get an array of 14 elements. The last one is 13, and we have port, flavor, behavior, and so on in here. And when we look at this, we can see, for example, that port, that exception 12 is null, 13 and 11 is the same value, 10, 9 is 0, then we have 8, 7, 6, 5, 4, 3, 2, and 1 have the same value, which is different from 11 and 13. And we have a 0 here for the port in 0, which is not surprising because it's empty. Okay, so knowing this now, let's try to figure out who owns this port. So when we look at this port, it's number 13 dot port. We dereference it, and we have basically a port here now. And let's have a look into the IP object. .IP object IO bits, and we look at this 03FF because that's the kernel object type mask, and the kernel object type mask is 0. So this means it's actually not a kernel object, so we can go forward and look at the other fields. So a port has an IP receiver normally, and this is a IPC space, so let's dereference the IPC space. And when we look in the IPC space, we see there's actually a task here that is connected to that port. So we can do is task. We dereference it again, and now we have the task that owns this port, that is the exception handler. And we want to know what the name of the port is, of the task is. So let's look into the associated proc structure. So that is bsd_info, also dereference this pointer. And so now we have a proc structure of the port, of who owns that port. And when we look into the proc structure, we have here the pcom and the p name. So that's basically launch D. So that means that launch D owns this port, which is not surprising because this is the ports that our crash, our report crash launch daemon works with. And of course, launch D is responsible for grabbing the exception ports of launch daemon, of launch daemons. So So that was this. Now with when we know this, we can have a look at the other ports. So again, now let's look at the number 1 and dereference the port. So we have the port here. We do the binary 0x3ff. Oops, sorry. No, we have to do IP object and IO bits. And then our icod type is kernel object 40. So now we have to figure out what is kernel object 40. So for that I have the kernel source code here, and we can now search for icod anything in .har, and let's find this here. So here we have our table of the types, and when we go to 40 we will see that it's icod UX handler, which is the type here. So let's search for that and find where it's implemented. And when we look at where it's implemented, we will see here that this is an object, a kernel object that is created for a Mach. Here you can see host set exception ports. So we are setting the handler here for the usual exception handlers, and then down here we have the actual handling code for the exception handling. And what this actually does is it basically makes Mach exceptions available as BSD signals. So that's the default handler for exceptions on macOS and iOS. Of course, it's usually overwritten by the daemon for certain exception types. But as you can see here, many normal exception types still go through the same way, so they get converted into BSD signals. Okay, so and this is what I wanted to show you. So this is how you find out what exception handlers there are. Now I leave you to it, and I wish you a great day, and see you for the next Advent Calendar Door tomorrow.